Welcome. Let us look at this quantity a little more closely, dou ut by dou ni at constant Vt, St and J. Let us define that quantity dou ut by dou ni at constant Vt, St and J as something called mu I, where mu I is actually called the chemical potential of species I. Note this term chemical potential, this is going to be a very important intrinsic variable in this entire course. So, please take a note of this. I will call this equation 2.11. Therefore, in terms of whatever we have defined just now, the chemical potential, we can write our equation 210 that we saw earlier as dut equals T dst minus P dVt plus summation of summation over I mu I dni. We will call this equation 212, excuse me. So, that was for internal energy. Let us follow a similar argument for the total Gibbs free energy G. Gt we know, rather let us take Gt as a function of temperature, pressure and all the number of moles of the components. So, N1, N2 till Nk, equation 213. Therefore, the total differential Gt dGt can be written as dou Gt by dou T at constant P all other Ni or all Ni dt plus dou Gt by dou P at constant T Ni dP plus, as we have seen, dou Gt by dou N1 at constant T Np and all other Nj's dN1 dou Gt plus dou Gt by dou N2 at constant T Np all other Ni's dN2 and so on, which can be represented in short form as summation of I over 1 to k, summation over I from 1 to k dou Gt by dou Ni at constant Tp Nj, where we already saw that I and j will not be the same, times dni. I will call this equation 214. If we compare this 214 with 2.8a, which is for pure component system or a single component system, dgt equals minus sdt plus vt dp, we can write dgt equals minus st dt plus vt dp plus the remaining term which comes in for the multi component case, since we have for a multi component case gt to be a function of all other components also, the amounts of components also. So, we have this extra term here, summation of mu I dni. We will call this equation 215. Let us define dou Gt by dou Ni at constant temperature, pressure and Nj, which is this quantity, as mu I itself. That is what I have done here when I wrote this equation. Somebody can ask me this question now. You had earlier said that dou ut by dou ni at certain variables being constant, st, vt and ni's being constant, nj's being constant, you had defined as mu I, whereas now you are defining dou gt by dou ni at constant tp and nj as mu I. How can you do that? Let us now go ahead and show that these two quantities are actually the same. To justify, let us begin with equation 212, where we first defined our mu I. We started with dut equals T dst minus P dVt plus summation of mu I dni. Let us add d of the total the differential of this particular quantity PVT minus T ST to both sides of equation 212. If we do that, dUT plus d of PVT minus T ST equals TdST minus PdVT plus the same quantity on the right hand side plus summation of mu I dNi. Note that we can combine these together, they are additive, the differentials are additive. You can visualize the differential in a graph or in a 2-dimensional graph or a 3-dimensional graph, then you can understand why this is additive. So if we recognize that this is additive and you can expand the term on this side using chain rule, let us do that. Therefore d of ut plus PVT minus TST equals TdST minus PdV we already had. Now if we expand the term that we added by chain rule, we have PdVT plus VT minus TdST minus STdt plus whatever remained there, which is summation of mu I dNi. We can cancel TdST and minus TdST. We can also cancel plus PdVT and minus PdVT, and therefore dGT equals minus STdt plus VTdP plus summation of mu I dNi. Note that this term automatically became dGT and whatever was left here was only minus ST dt plus VT dP plus summation of mu I dNi, and this was the same mu I that we started with earlier, we did not do anything to it, and therefore the mu i's in equation 211, which was for the internal energy dUT, and equation 216 for the Gibbs free energy dGT are the same. So they although we had used different ways to define the chemical potential, they all turn out to be the same quantity. Let us look at this equation 216 a little closer. It is a very useful equation. Dou GT divided by dou GT by dou Ni at constant temperature, pressure and all other mole numbers remaining constant, we had defined as mu I. Note that we have defined mu I in the context of a multi-component system, that is purely didactic, that is purely to facilitate a certain flow in the development of the subject. The chemical potential itself is an intrinsic quantity for a particular system, and therefore whether the system is multi-component or whether it is a single component or whatever other combinations you may have, the concept of chemical potential is still valid for any system that you take. Okay. To put it a little more formally, written here, although the chemical potential mu I was introduced in the context of a multi-component system, it is an intrinsic thermodynamic property, thus it is an equally valid concept for a pure component also. Let us look at this a little closer now. Look at the quantities that are being held constant in this definition: dou GT by dou Ni at constant temperature, pressure and all other Nj's different from Ni, which is taken for the differentiation. These are very easy to maintain constant in an experimental situation, and therefore this definition of chemical potential has significant experimental relevance, and because of that, although you could define chemical potential as dou ut by dou ni at certain variables constant, dou at by dou ni at certain other variable constant, and so on and so forth, this definition is most commonly used. I have already mentioned this, but let me complete the definitions here. So by extension, as mentioned earlier, we can define chemical potential in terms of enthalpy H or the Helmholtz free energy A. Therefore, for a multi-component single phase system, dut equals T dst minus P dVt plus summation of mu I dni, equation 212. We are just compiling all the equations together, we will have it at one place for easy reference later. Dgt equals minus St dt plus Vt dP plus summation of mu I dni or all I, equation 215. Dht equals T dst plus Vt dP plus summation of mu I dni, equation 217, and dat equals minus St dt minus P dVt plus summation of mu I dni, we will call this equation 218. What I would like you to do is to actually sit down and verify the same way that we did that these two mu i's were the same. It will be good if you verify and convince yourself that these two mu i's are also the same and they are the same as the other mu i's that are here. That way there will be no doubts in your mind. These are the 4 equations that we have just derived. I would like to point out some interesting features here. These 4 equations, dut equals T dst minus P dVt plus mu I dni, dht equals T dst plus Vt dP plus mu I dni, dat equals minus St dt minus P dVt plus mu I dni, and dgt equals minus St dt plus Vt dP plus mu I dni, summation. Let us look at it in terms of writing a total differential in terms of its partial differentials. This term, as you can recall, can be written as dou ut by dou st at constant Vt ni, and both these held constant, and this term can be written as dou ht by dou st at constant P and ni. Similarly, this term P can be written as dou ut by dou Vt at constant St and ni. The same P here which appears in this other equation can be represented in terms of the Helmholtz free energy as dou at by dou Vt at constant T and ni. Now you get the scheme with which we are going to do things. Minus St is dou at by dou T at constant Vt and ni. Let us look for another St. It is here, St minus St equals dou Gt by dou T at constant P and ni. Similarly, this Vt can be written as dou Ht by dou P at constant St and ni, and Vt which appears here can be written as dou Gt by dou P at constant T and ni. And as we have already seen, the chemical potentials can be written in terms of either the partials of ut with ni at constant St, Vt and all other nj's. Here in terms of enthalpy, you could write mu I as dou Ht by dou ni at constant S T V T and all other Nj's, dou AT by dou Ni at constant T V and all other Nj's, and dGT at constant dou GT by dou Ni at constant Tp and all other Nj's. If we put this all together in one place, we can say our temperature can be represented as the partial of ut with respect to St at constant Vt Ni, or partial of Ht with St at constant P Ni. Okay, we had seen T appearing in two different equations there, and which represented which we represented as partial derivatives. I am just compiling those here as equation 219, P as minus of dou ut by dou Vt at constant St Ni, or minus dou At by dou Vt at constant T Ni, equation 220, St as minus of dou Gt by dou T constant P Ni, or minus of dou At by dou T at constant Vt Ni, equation 221, and Vt as dou Gt by dou P constant T Ni, or dou Ht by dou P at constant St Ni, equation 222, and all the four ways of representing the chemical potential as either dou ut by dou Ni at constant Vt St Nj, dou Gt by dou Ni at constant Tp Nj, dou Ht by dou Ni at constant St P Nj, or dou At by dou Ni at constant T Vt Nj. Let me call this equation 223. These are very useful equations, as we will see you in the next class.